Okay, so let's proceed with the last section of this chapter, air conditioning process. Okay, okay, the last one is the cooling tower. Okay, so this is a cooling tower. The purpose of cooling tower is if you have a large amount of waste heat, okay, that need to be reduced. For example, the heat is actually come from an industrial power plants. Okay, the load is actually very high. Okay, let's say something like this. Okay, let's continue this one. For example, let's say if you have a refrigeration process, okay, you have a compressor, when and after that you have a condenser, and you have expansion valve, and after that you have a evaporator, and goes back to the compressor. So this is state number before compressor, state number 1, this is state number 2, state number 3, and this one is state number 4, right? Okay, now this is actually condenser, right? Because after compressor the temperature is very high, so this temperature need to be removed from the coil, hot coil or heating coil, okay, before it goes to the expansion process and cools down to perhaps let's say you have a machine, for example, or perhaps a room, very hot room, needs to be cooled down, so the temperature will go into the cooling coil, so it's gonna increase by the compressor, and later it's gonna be reduced. So here, due to perhaps the Q load here is very high, okay, so we need what we call as a cooling tower. Okay, so of course engineer already decide that we want to use a cooling tower to reduce the temperature of this condenser. So you have perhaps a medium or a room here filled with water, for example, okay, so it goes into the room and cools down the heating coil, okay, which is the red color. So that's why this is a low temperature cool water. Okay, this one is cool water, goes into the system, and after that it's going to be this cool water, due to the existence of this cooling heating coil, is going to increase the water temperature, so it goes back to the cooling tower, right? So that is the purpose of cooling tower, especially if you have a big amount of waste that you need to reject to the atmosphere. So of course we are not gonna analyze this one. Our main concentration will be, our main focus will be to the cooling tower. Okay, so let's go to example. Cooling water leaves the condenser of a power plant and enters a wet cooling tower at 35 degrees C at a rate of 100 kg per second. The water is cooled to 22 degrees C in the cooling tower by air that enters at 1 atm pressure, 20 degrees C and 60% relative humidity, and leaves at saturated at 30 degrees C. Okay. So neglecting any power input, determine the volume flow rate of the cooling tower and mass flow rate of the required makeup water. Alright, so let's draw a cooling tower. Okay. Okay, cooling tower, we're gonna have something like this. Alright. Okay. So underneath the cooling tower will be filled out with water. Okay, this is water level. Alright, here is where the air, right, from the outside into the cooling tower. Okay. So into the cooling tower we have water. Okay. Right, this water is going to be sprayed down inside the cooling tower. So this is supposed to be warm water, right? And you have a fan here. So in the end, your air from the bottom of the cooling tower will move to outside. Right. And then this one, you have a pipe. Back towards the system. Okay, which is this one. And you have a what we call as a makeup water. Okay. So this goes back to the system. This is the makeup water. Alright, so this one is cool water. Cool water. So this water is being cooled back by the air, right? So this one we have warm water. Okay. and then this water is being sprayed down into the cooling. Okay, that's how this warm water is being cooled down. Okay, it becomes mist. Basically, mist is easier to be cooled down, so you have an air cool down the mist, and it's going to be filled at the bottom. So this is actually cool water at the bottom, and the hot air will move out from the cooling tower. So that's the purpose. That's how cooling tower works, right? Okay, let's do the balance equation. Number one is dry air mass balance. Okay, for dry air, we only have two. Okay, we have two fluid here, right? Okay, we have dry air, which is this one, and then this one. Meanwhile, we have another fluid, which is the water itself, which is in the pipe. So this one is water, and this one is actually water, right? So for dry air mass balance, okay, let's say we put first all the values related to the problem. Okay, this is state number one. So occurs at 1 atm, 20 degrees C with relative humidity 60%. Okay. Next is the information on dry air, 30 degrees C. So this is for state number 2, 30 degrees C, and relative humidity 100%. Next is warm water condition. Okay, we put at state number 3. So this one is 35 degrees C, and the mass flow rate of water 100 kg per second. And then we have a cool water, which is 100 kg per second. And then the temperature, so this is state number 4. State number 4, the water is cooled to 22 degrees C in the cooling tower. It's cooled to, okay, 22 degrees C. This one is 22 degrees C. Okay, so that one is state number 4. So when we're talking about dry air mass balance, meaning only state 1 and state number 2, right? So m dot a1 not plus, this is not mixing chamber, m dot a1 equals to m dot a2, which is actually equals to m dot a. Okay. Everything that goes into the cooling tower must goes up, air, right? Alright. Next, water mass balance. Okay, so for water mass balance, we have at 4 positions, at 4 states. State number 3 is obvious because warm water into the system. State number 4 is out from the cooling tower. State number 1, since air also have portion of water vapor, right? So meaning that one is considered as a water as well. Same with state number 2. Air have their own portion of water vapor. So for water mass balance, m dot 3 plus m dot a1 omega 1 equals to m dot 4 plus m dot a2 omega 2. Okay, we have into the system. Okay, into the system is warm water m dot 3, right? And m dot a1 omega 1, which is the portion of water by dry air, okay, by state number 1. And then we have out from the system, which is we have m dot 4, okay, m dot 4 out from the cooling tower. And then we have also dry air out from the system, so meaning m dot a2 omega 2, right? Okay, next I'm going to talk about this part, which is the effect of makeup water. So why we need makeup water? It's because of, okay, since this is open system, right? Even though this is actually inside the cooling tower, but the thing is the water is being sprayed into the cooling tower and being cooled down. So there is a case there where the volume of water is reduced, correct? Because the water can be pushed out from the cooling tower itself. And due to what? Perhaps due to the movement of air, so due to evaporation. So that's why if there is no makeup water, so in the end the system, the water volume will be reduced. So we need to make up back the water to ensure that the volume of water maintained within the cooling tower system. So what happened is we have this equation, right? So this one, this portion, you might want to look something like this, right? So this is makeup water, right? So this is the one that comes from the cooling tower. Okay. So this one is state number 4. Okay, this is makeup water, and this is the one that moved back into the cooling tower, right? So this is actually state number 3. So the balance of this is actually m dot 3 equals to m dot 4 plus m dot makeup water, right? So m dot 3 out of it, so this one into this one, so m dot 4 plus m dot makeup water is actually equals to m dot 3. Alright, so when you rearrange this equation, into something like this. M dot 3 minus M dot 4 equals to M dot A, right? Omega 2 minus omega 1. Okay, because here is, as you can see, M dot A1 equals to M dot A2 equals to M dot A. So when we rearrange, this one becomes M dot A omega 2 minus omega 1. Okay. So this one also equals to M dot make up, right? Okay, next we go to the energy balance. Okay, so for energy balance, we have energy in M dot H equals to energy out M dot H. So if you see here, the one that move into the system is M dot A1 and then M dot 3. Out from the system is M dot A2 and then M dot 4, right? So what you're gonna have is into the system M dot A1 H1 plus M dot A3 H3 equals to M dot A2 H2 plus M dot 4 H4. So since we know that M dot 4 is equals to M dot 3 minus M dot make up water, okay, so which is come from this equation. So, right, so we substitute that value, that equation, into our energy balance equation. Plus this one is M dot 3 minus M dot make up particular with H4. Okay, all right. Okay, next what we want is we want to find M dot A. Okay. Okay, this one's supposed to be M dot 3. M dot 3. Since this is not dry air, state number 3 is the water itself. So it's not going to be M dot A3, it's going to be M dot 3. For water, there is no dry air, just directly M dot 3 or M dot 4. Okay, so this is M dot 3. And then since we know m dot a1 equals to m dot a2. Okay, so basically we can rearrange this equation, becomes m dot a is actually m dot 3 h3 minus h4 divided by h2 minus h1 minus w2 minus w1 multiplied with h4. Okay, so from there we can find the mass flow rate of air. Okay, so then from the mass flow rate of dry air, we can determine the volume flow rate of air into the cooling tower. So V dot air is actually equals to m dot a multiplied with specific volume. Okay, so we can use at any states between 1 and 2. So we can use v dot 1 equals to m dot a multiplied with specific volume at state number. Right. So next, what we want is actually we want to find all these h value, h, omega, and r. So let's get back to our problem. Okay, so we need to have psychometric chart. Okay, so from state 1 and state 2, we can use psychometric chart. So state 1 is 20%, 60% relative humidity. So let's take a look. 20%, so 20 degrees C. Right. 20 degrees C. So this one is 20 and 60% relative humidity. So this is state number 1. Okay. So from there, we can determine your enthalpy and then your omega, and then after that your specific volume, right? So for state 1, this one equals to 42.2 kilojoule per kilogram dry air, and then omega 1 equals to 0.0087 kilogram H2O per kilogram dry air. Then the specific volume is what? 0.842, right? So 0.842 meter cube per kilogram. Okay, next we determine state number 2. State number 2 is 30 degrees C, 100% relative humidity. So if it is 100% relative humidity, so it's at the saturation line. Okay, so meaning this value, right? So this one, 30 degrees C, 100% relative humidity. Okay, so if you notice, just additional information, at 30 degrees C, the wet bulb also 30 degree. This one, wet bulb, right? Wet bulb also 30 degrees C, and the dry bulb also 30 degrees C. If you look here, it's actually 30 degrees C. So everything at 100% saturation line, the dry bulb, the wet bulb will be the same with the dew point temperature. Okay, just some additional information. Okay, now let's find the information at this point. Okay, what we want is enthalpy omega 2. Okay, so perhaps the volume if needed. Okay, for state 2, enthalpy 2 is actually 100 kilojoule per kilogram dry air. Omega 2 is 26, 27. Okay, here the value given is 0.0273 kilogram H2O per kilogram dry air. Right, next is V2. So V2 is 0.89897, right? 0.897 meter cube per kilogram dry air. Okay, 9796. Alright. Okay, that is state number 1 and state number 2. You can find this value using psychometric chart, since the problem is actually 1 atm. Okay, normally cooling tower is positioned at atmospheric temperature. Okay, so even if not stated, you should know that cooling tower in real application always positioned at the ambient position or atmospheric pressure. Okay, let's proceed to find value of state number 3. State 3 and then state number 4. Okay, state 3 and state 4 is water. Okay, this one is air. So for air, since 1 atm, we can use psychometric chart. And for water, it's liquid. Alright, liquid. So for state number 3, the temperature given is 35 degrees C. And state number 4 is 22 degrees C. Okay. So at 35 degrees C, at 22 degrees C. So we need to refer to the property table. So for state number 3, the value we need to use is HR, enthalpy for liquid. Right. So for 22 degrees C, this is 22. Okay, you need to do some interpolation to get this value. right? 435 is directly given here. So page 3 is equals to, what's the value just now? 146.64 kilojoule per kilogram. And for the saturated liquid at state number 4 is 92.28 kilojoule per kilogram. So this is actually H4. Okay, so basically you have all the values required to find M dot A. We have H3, H4, H2, H1, omega 2, omega 1, H4, and also M dot 3. So we can determine M dot A. Okay, so M dot A is 96.9 kilogram per second. Okay, next is we want the value of V dot 1. Okay. M dot A available, we just found the value, and then V1 specific volume for state number 1 is 0.84842. So V dot 1 is 81.6 meter cube per second, right? Okay, B. So for B is determine the mass flow rate of makeup water, M dot W. Okay. So we can use the equation of makeup water. Okay, so we can use this one. Since we already have M dot A, omega 2 and omega 1. So from there, B is M dot makeup equals to M dot A omega 2 minus omega 1. Right? So we have the value here, right? And then M dot A, we just found the value. Okay, so M dot makeup water is 1.8 kilogram per second. Alright, so done. Okay, we're done with the cooling tower. Okay, so I think that's all for this chapter, right? Okay, the property table and the psychometric chart is actually from thermal engineering books. Okay, they produce from McGraw-Hill. Okay, from book by Chang'e. Okay, based on heat and mass transfer fundamentals and application, and thermodynamics and engineering approach. fourth edition and seventh edition respectively. Alright, so I think that's all. Assalamualaikum warahmatullahi wabarakatuh.